Okay, yeah, thanks. Good afternoon, everyone. Thanks for coming. My name is Allan. I'm a support engineer at Engineered and Days. We have a booth there. We make the Helm and workflow. Today, I'll be talking about autoscaling and how you can make your own with a bit of math. This is a bit of a personal, academic-ish project of mine that I mess around from time to time, so yeah. A bit about me, I wrote a Docker book last January, so it's been out for a year now, so it's mostly obsolete. Right. I also wrote the chef cookbook to launch a Kubernetes cluster, so I made custom chef resources, so if you want to learn more about it, you can look me up in the hallway afterwards. So today, I would like to talk about how we typically run and operate distributed systems. So typically, we have ops staff, and we manage a server farm that receives traffic. And so, for example, we monitor the CPU usage, and then the actual usage gets fed into our monitoring system, like Hipster, and then PagerDuty wakes it up at 2 a.m. And then us as an ops person wakes up at night, then check if CPU utilization is too high or too low. That's why we got alerted. So we check if our goal is different from the actual reading. And then we log into our fleet of servers or our cloud provisioning API and spin up more instances. So you can see we have a similar structure for your air conditioner. So here, in an air conditioner, thermostat basically regulates the coolant, which releases cool air, which makes your room cold. So you have your room temperature, the weather, and then it gets affected by the coolant of the air conditioner, and then we get an actual temperature reading from our sensors, and then the thermostats read that. And then it compares with the temperature we set in the thermostat and to the actual temperature. So if it's too hot, then it releases more coolant. If it's too cold, it releases less. So the difference here is that your air conditioner doesn't have an ops team that gets paged to adjust the coolant, right? So we have this automation now, right? So we have, in Kubernetes, you have your horizontal pod autoscaler, which basically allows you to set the number of replicas in your replica set or replication controller depending on the reading of the CPU utilization from Hipster. So you set a target on your HPA object and you scale it. So we have that already. It's working properly. So one of the things that you can do is you can try to customize it, but the current object only has so much. Also, by knowing the first principles on how an autoscaler works, then you can know if your autoscaling policy is effective, or is it stable, is it working as expected, or is it working good enough? So the math behind the air conditioner, called control theory, can help us figure out that. So control theory is a discipline developed how systems are dynamically affecting each other. And using that information, you can use that to create feedback loops to correct the target behavior. And then there's a couple of results in math that describes how effective your feedback loops are. So control theory was developed in the early part of the Industrial Revolution. So the core part in the Industrial Revolution is the steam engines became more reliable by having consistent performance. So this centrifugal governor was made in order to regulate a steam engine. So a centrifugal governor works by having a spinning disk connected to the engine. So if your engine is fast, this will rotate fast. And that spinning wheel is connected to two fly balls that will rotate. So the faster these two weights rotate, then it will go up. And then when it goes up, it manipulates some levers that's connected to a valve that regulates the steam intake. So if your steam engine is too fast, so the weights will go up, and then it will close the valve. So the amount of steam getting inside your steam engine is lower, so it will try to slow down. So this produces a self-correcting behavior. So that the centrifugal governor was invented around the 17th or 18th century, but then people did not really know how it works. So it's only in the 19th century where people got the theory figured out. So you can say that during the Industrial Revolution, people have been cargo culting technology for 100 years or more. So we're doing pretty good as the tech industry. So in control theory, there's architecturally a few basic parts. So you have your target input, the set value. So in an autoscaler, that's what's our target CPU utilization for our system. And then in the air conditioner, that's the set temperature in our thermostat. Then you have the output, which is the actual one, so the current CPU utilization. And then next, you have the control input, which is dictating the number of replicas your autoscaler sets. And then the traffic in this case is just modeled as a disturbance. So the traffic going to your servers will change the CPU, and then it will your autoscaler will react according to that. So there you have the basic structure. So this is a simple code that I wrote to illustrate that. So you have your output value that's read through a sensor. So in the autoscaler I wrote, it reads off the value of heapster. And then from the output value, the CPU utilization, I get the number of instances or the number of replicas using my controller. And then I have an actuator that basically makes an API call that sets the instance. Then next, I have a control loop to periodically send off the values to my monitoring system. And then I do that every 5 seconds. So that's the control monitoring interval. So this is an example of how it works. So I have my own autoscaler, not the one built in Kubernetes. So you have the blue line, which is the CPU utilization, and then the green is the number of replicas. So at this point, I increase traffic, which correspondingly increased CPU, and my number of replicas increased correspondingly. Same goes when I reduce traffic, then CPU goes down as well, and then the number of replicas follow. And I'll show that later on in a small demo if we have time. So why does like this simple autoscaler work? So in systems, you can make a simple model if it's linear and time invariant. So as you scale up and down, then it's not affected when was it scaled up or down. The effects are the same. So in control theory, you can model your autoscaler as these equations. So these equations are the same. They're just, one is analog and one is a digital form. So basically, Y is the output, which is the CPU utilization. and then U is the control input, which is the number of instances. So this equation just says that the number of instances you set in your replication controller is dependent on the CPU utilization and a proportion of it, and the change in CPU utilization. That's why there's a derivative written there. In the digital form, so that you can code it, you can model it such as the CPU utilization at the next monitoring cycle is dependent on the current CPU utilization now and the number of instances you set now as well. Okay, so once you make a model of your system that you want to autoscale, then there are like 4 desired properties that you want. So even though you're not making your autoscaler, you can use these criteria to evaluate the built-in horizontal pod autoscaler you set in Kubernetes. So first is stability. You want your scaling to be stable over time. So here is an example of an unstable autoscaler. So at first, CPU usage increased, so you add more instances. But then you added too much, so you scale down. But then you scale down too much, so you try to add more. And then you remove instances. Then you keep adding more. So in the end, like you keep adding more, and then reducing more and more, which makes an unreliable performance. Because at one point, you'll have 1,000 instances, and at some point, you have 1. So unless your traffic is really like that, then it doesn't make good of a system as it should be. So this is also another example of an unstable one. So no matter how many instances you add, like your utilization still goes up through the roof. So there's probably other problems in your application, like the networking or the database you depend on if such a thing happens. So this is sort of stable, but then it oscillates through. So you have the dashed line, which is your target performance, but then it oscillates through like too much instances and not enough instances, but it's within a certain range. So it's stable, but not yet quite there. Then this is what you want. So basically, as time goes on, then the error margins starts to decrease, which is a stable system. So here is another stable version, which is a smoother one. So it gradually goes there. So a problem with this, sometimes it's slow. And okay, before I go in the slow, like another property is you want it to be accurate. So it goes through the target performance at some point. So I want to go to, let's say, 70% utilization. Then after some point, as you scale up, then you go back to the target value of 70% performance. So when I talk about the system being slow, so when you scale out instances, you want to settle to a value that's fast enough to your target performance. If it's too slow, then it means in autoscaling, if you didn't have enough instances, then you already lost traffic. So you want it to be fast in terms of settling time. Then remember the oscillations I showed earlier. So you also want your system to not have overshoots, which means you overcompensate and then you go back again. In some designs of autoscalers or controllers, you may want that as a trade-off so that it responds fast with a faster settling time. But depending on, I guess, your budget, because you added too much instances, then you will probably not want that in your system. Okay, so let's go to the autoscalers and how you can make one yourself. So here we have our, this is basically the replica controller. And then this is our autoscaler, C. So basically, to figure out the number of instances to scale, we need to get our goal, which is the reference value, and then the current value. So the target CPU and the current CPU, and get the difference of that, and that would be our error. And then use that error to get the number of instances using some like some kind of function. So later on, I'll show what functions you can use in making controllers. So the first one is a proportional controller. Basically, the number of instances you set is the difference in CPU utilization times a constant value. So here's a graph of that. So for example, this is your target CPU utilization, which is, let's say, 70%, and you're currently at 60%. So it means you need to add less instances. So you add a bit of that, and then your number of instances will decrease. The graph is inverted, but so there's an overshoot, and then at some point it will settle down. So this controller has certain properties. Like the higher you set your proportional gain, then you'll have more overshoot, but then you can settle down faster. But then proportional controllers have a limit of having a large error margin in the end. So the value will settle, but it's a bit off your target. Next, okay, I talked about that already. Yeah. Next, we have integral controller. So basically, the number of instances is dependent on the number of instances you have previously plus the plus an error value. So basically, you're averaging out the errors over time and then multiplying that. So if you're averaging your observations, then it means you're reducing the error difference. But then since you're averaging as well, then your system becomes less responsive. So another controller you can use to make it more responsive is you check for the change in error. So if your CPU utilization changes very fast, then you can respond to it very fast. But since it's fast, then it's also very sensitive to noise. So in practice, people combine their proportional, integral, and derivative controllers to get the performance they want in their controllers, or in this example, our autoscalers. Okay, so I discussed all the types of controllers you can use for your autoscalers. So you have based off the model, but then in the end, computers are not like fully deterministic. So there's non-linear behavior as well. So if this was a perfectly linear time invariant systems, then as I increase my number of replicas, then my CPU utilization should decrease proportionally. But then in some observations in generating my model, it's not the same value here. So there's like outliers here. So even though I model it as a straight line, there are error margins. So there's a need to reevaluate the model to check if it's really effective. So the same goes if you're using Kubernetes built-in autoscaler. So you want to check if the values you set, the target values you set in the HPA object is making sense for your application. So you can use control theory not only in autoscaling. So people have done like auto-tuning and auto-configuration before. So for example, people have configured their Nginx or Apache services wherein they adjust the keep alive timeout in response to the response time of the application, or in a or for Nginx, like the memory versus the number of worker connections. So your queue is adjusted. And then you can combine these parameters together to make more sophisticated multiple input and multiple output systems. So in summary, control theory is a model you can use to iterate on the feedback being received from your monitoring system. Then control theory also gives you a math framework to show if your feedback loops are effective. Also, simple models can go a long way as well. But then in the end, like, it's also important to keep reevaluating your models if they are effective. So if you want to learn more about control theory, these are two books I recommend. The O'Reilly book on the left is a good introductory book. It has like simulations in Python that you can test out. The blue book shows like very concrete examples. So that's where I got the keep alive timeout and response time auto configuration. But this is like more like rigorous textbook-ish academic stuff. But if you want something concrete to do in your experiments, then this will get your feet more wet. Just a few acknowledgements. The demo I'll show later and the benchmarks I did before were run on GKE through developer relation credits provided by Kelsey Hightower. Okay, I'll show a bit of demo. So here I have my application, which basically serves a web app request. And then I have a load generator. So this looks like the 1 million requests per second demo from Kubernetes, from KubeCon, I think last year. So first, we need to generate our model. So I make a model by setting the number of instances up and down using a simple sinusoid. So basically, this is a graph I use to generate my model. So basically, I scale up and down the number of instances against constant traffic, and then the CPU utilization responds inversely. So you can see that it's not a perfect counter sinusoid. So that's why there's nonlinearity in the behavior. So to show that I'm not using Kubernetes built-in autoscaler, I'll just show that. Okay, I'll just show off my sleeves are empty, right? So after generating the model, after getting the data, we generate a model. So I just made an R script that basically generates the model from the data. So I get my model. So basically, our model is that the CPU utilization is, at the next value is 0.94 of the current utilization and minus 0.2 of the number of instances. So so we'll use that, and then we'll use that to identify what makes our controller stable. So I already made a controller for that. So here's the controller loop I showed earlier, and this is the controller. So basically, I set my proportional gain to minus 0.1 and my integral gain to be 0. So it's a simple proportional model. And you can see my controller here. Okay. So basically, the number of instances is the proportional gain times the difference in CPU utilization. Okay. Okay, so I'll just show that these libraries here are simple API calls through Kubernetes. So our sensor that gets the CPU utilization is a basic API call to Hipster. So it gets the list of number of pods in our object, in our application, and then gets the CPU. And then the actuator, the one who sets the number of instances, is just an API call to the replication controller. So you can see our controller running here. So it's taking a reading of the CPU usage and then setting the number of instances. So you can see here. So here I have 71 instances at 270 CPU cores, or is that milli CPU cores? Whatever Hipster is giving you. So that's that. And then it's receiving traffic at 20,000 queries per second. So I will scale. So currently I have 20,000 queries per second. So I will double that to 40. Okay. Double that. So we'll just wait a bit for the number of requests per second to go up. And then we can check again on our monitoring system. Come on, work. Okay. Okay, so the request per second is starting to pick up now that we've generated more load generators. Next, we'll go on to our controller. So the CPU utilization will then start to increase because we're sending more requests. So currently it's at 273. Then later it will increase as the number of the pods in our replication controller starts receive more traffic, then it will start to consume more CPU reserves. So there you have it. We're now at 400% CPU usage, so we can check our autoscaler here. So the number of CPU increased, and then our number of instances is increased correspondingly. So, yeah. And then when I scale it down, okay, so once the traffic decreases, then the CPU utilization will go down. So we can just confirm first if our traffic goes down. So it's starting to go down. Let's wait a bit more. Okay. You can just not wait for it. So that's part of like controller design as well. When do you want to respond? So you can also model the delay in your measurement. So the reporting in Heapster doesn't really register right away when you add more instances. So there you go. So it won't register the CPU. So sometimes there's delay in the control loop as well. So when designing controllers, you can model that and design around that as well. So if you want to check it out, it's in my GitHub account. So it's Espinosa/control theory. So you can play with it. So that's it. Thank you for listening. And I can take questions. Anyone have some questions or something? Yes?
Do you actually know which model does the default autoscaler fit?
Yeah. So the default, I looked at the autoscaler code while working on this. So again, sorry. The question was, what's the model being used in the default autoscaler? So it's sort of a proportional controller. If you look at the code, it's basically they check the CPU utilization, and then the number of instances is, I forgot what's in the code, but it's, I think it doesn't do averaging of some sorts. It does averaging at the monitoring level, but so if you probably put the model together, then it can have an integral component. But if you look at just the control loop, not the sensor reading one, then it's mostly proportional. Yes?
Is it possible to simulate games such as a Pokemon Go, like using this?
So the,
model based on the data.
right. So the question was, is it possible to generate, to make models using real-world data like Pokemon Go? So, so when I made the sinusoid, like this was, well, I pre-recorded it, but I scale up and down the instances against a certain load, and then I get the linear relationship. So when you want to get a model from the real world, then you basically get the two metrics you want. So for example, you have your Pokemon Go load, so you get it from your access logs, right? Like the request per second, and then you get the other variable, which is the CPU load, and then you basically do a linear correlation between two. So you just basically all the data you have there, you just plot it on a scatter point.
So how much duration of the data do you want to be precisely predict?
Right, right. So yeah. So the thing about control theory is that, so for example, a proportional model doesn't really take samples. So it's pretty much set. And then you can, yeah, haven't really thought about that. But yeah, so if you have data, then it only works in a certain region. So you design against that operating region, and then just get enough data around that operating region. So like your typical operating case, right? And then, but then if your traffic loads too much, then your model is already invalid. So you need to regenerate. Yeah. So I think some people are doing that. So they combine multiple control loops. So they have a the fast loop, which does the actual auto-scaling, and then there's a higher control loop, which gives parameters to the controller based on other data, which is sampled at a larger amount of time. So they do that kind of model combinations. Yeah. Cool. Yeah. Anyone else? Yeah, so thank you, everyone. Oh, there's one.
Is there any way to introduce predictive control that predicts the behavior of the number of queries that will come and select the scale beforehand? Because all the controllers that we presented are kind of reactive, so they will
Yeah.
scale the number of the chart of the there, and then it will activate the new number of
Right. So the question was, can you make a more predictive control loop? So the answer there is that, so what people do is, like, for example, you're planning an event, then they change the target value. So in my normal operation, I'm targeting 70% utilization, but then for the weekend, for example, for Black Friday, I change my target to 40%, and the system will respond correspondingly because you change your goal. So another one, so the one I mentioned where you have multiple cascaded control loops, so they use that setup to change the target as well. So you can do a more sophisticated model that way. Yeah.
So in that situation, would you just have like your outer control loops measure something
Else, yeah.
or even just an arbitrary like math set
Yeah.
this week?
Yeah. It can be just like an open control loop, which you basically set the levers manually. So in that case, your outer control loop is actually a human. So, yeah. So, yeah. Thank you.